Hello everyone, we meet again to start with chapter 4. We have seen the attitude kinematics in chapter 3, so we know what kind of coordinate systems we have been treating in chapter 3, and chapter 4 is going to start off a very basic thing, which is going to look at the basic, simplest control approach that normally is being taken by not a very expensive satellites. Typically, low-cost satellites at the moment using a passive way of stabilization. So if you can look at this, is a gravity gradient stabilization that we're going to talk about in chapter 4, because it's one of those I think most low-cost and most I think common in small satellites that you always use. Now, when I say gravity gradient stabilization, we know for the fact that we are bounded by gravity, pull out gravitational field. So therefore, it is actually pulling us towards planet Earth. But don't forget, when we cleverly can use this, we can also do stabilization in a way. So therefore, let's see how actually we can do this stabilization. So if you can look at our planet Earth, just a simple diagram. Now, I define COG, center of gravity. Assume this is actually a rigid body. Let's say this is a planet Earth, where IJK, a rigid body. Let's say this is your XYZ or body coordinate system. Arbitrary. All right. Now, within this body coordinate system, you can imagine if this is the center of gravity of a satellite, the satellite can be maybe as big as here, right? It can have mass here, and so on. So I just pick an example of a mass here. So having this, I call a mass here. Having this particular mass, I'm going to see how this particular mass is going to affect this whole system, and I'm going to write an equation to it. So the basic thing is that I define from center of planet Earth up to the center of gravity, Rs, is the distance, radius. And from center of gravity to this particular mass within the satellite. This mass is actually the satellite, belongs to the satellite. And it could be, let's say, a tank, a fuel tank. It could be, a reaction wheel. It could be an antenna. Okay? Yes. But the distance here I define R1, but the distance is very small as compared to the RS from planet Earth up to the satellite compared to what is within the satellite. So it's very small actually. But for discussion purposes, yes, we will say that Ri or RBI is equivalent to Rs plus with R1. Just for a discussion purpose. So this is the exact I would say scenario that we want to analyze, because this is what our satellite is going to. Alright, I define. I know for the fact I've been exposed to gravitational force. I know gravitational rules. I know gravitational law. So I can write easy equations like this. The force, gravitational force is nothing but with respect to gravitational constant is a function of gravitational constant itself. And don't forget, this is basically the vector and the magnitude of basically the RL. That means the length of it. So we are actually subjected to that. We are a function of that. And obviously, the mass actually comes into play as well, because the more mass actually you have, you are subjected to the gravitational pull greater. And the nearer that you have, as you can see, the nearer that actually you are, the force is actually becoming more. The further that you are, the force becoming even lesser. So we understand this. Likewise, the mass side. Let me say, okay, if that's the case, what about our torque? Well, our torque, we can actually define is basically once the force has been found, practically if you have a distance acting, that means the cantilever distance of R, that should give you a torque. Now, more important, please do remember, this is a cross product. That means I have a vector R, I have a force vector, both are vectors, and this is a cross product. I should be able to get my torque. And here, this is actually a I would say derivatives of torques. That means what? Uh, well, I would say deviation of torques. That means the torques actually is going to change with respect to time. Right? I want to find an absolute torque. So it's very simple. I do an integration. When I do integration, I should be actually arriving to a simpler field. But I can reduce this as well. As I mentioned just now correctly, my RL, this is RS plus RI. My RS is so huge compared to even the small distance that I've shown just now, which is the R. So therefore, I can conveniently reduce an equation which goes like here. The actual gravitational torque I define as mg is a basically vector, nothing but proportional also to the gravitational constant, and basically very dependent also the distance and the inertia. In this case, basically I have defined, since I have the R is so huge, I just say that okay, fine, let's the R hat actually is a unit vector. I define that and I write in this form. I can actually open this up so that let go further. I open this up, this equation, and this is how you see. Same equation, 3 by 3 matrix, 3 by 1, 3 by 1. X component, Y component, Z component. Roll, yaw, roll, pitch, yaw. Okay? So what we see here is this. When you look at, remember, because of the R we have defined, R hat we have defined as a unit vector. So therefore, I should be able to basically see how this unit vector is actually is going to react, or rather is found in this particular equation by how we have also gone through a linearized equation of motion earlier as an exercise, and we know for the fact how are we going to actually transform basically a particular vector. Let's say a 3 by 1 maybe vector from a local vertical with respect to actually local vertical, local horizontal system to a body system. And this basically the matrix actually we have already found and used to develop our Euler equation of motion. So I will evoke that equation again. So in this case, what I'm saying is that, all right, let us see how am I going to solve this R2 and R3. Now, what I know, my rigid body at a unit vector is R1, R2, R3, X, Y, Z. That is quite clear because, but I know for the fact my RS is coming from planet Earth to the spacecraft. When I look at that particular vector from where I am in local vertical, local horizontal. I see there is only one thing is coming out. It is coming out through a Z axis, right? Because RS is coming out from Z axis. Go the other diagram, please. Diagram. Yeah. This is practically coming out from planet Earth, zenith. And I have always a nadir pointing because my Z is always nadir. So it's actually an inverse. Go on, right? So therefore, by looking at my LB and H, it is exactly that. Is a -1 of Z. Alright, good. Now this is a unit vector, right? 3 by 1. Conveniently, I'm using the matrix which we have used before for our Euler equation of motion in order for me to express local vertical, local horizontal coordinates into a body coordinate. So I'm going to transform this into a body coordinate. 3 by 3 matrix. 3 by 1, 3 by 1. And if If I solve this, I have R1 is phi2, R2 is negative phi1, and R3 is minus 1. Inject back into here, I would have a very reduced form. Now, if you look at it, R1 and R2, it's become very small. So, you can neglect that because it becomes very, very small, this term. So, we can keep a very simplified term by saying that, look, this is you have my roll, you have my pitch, and yaw is almost known. Yes, because why? Z is your yaw. You are, technically speaking, you're parallel basically with the actual gravitational pull. So you have a very, very slight. Obviously, not all the fields are basically parallel to you. If it's a sphere, the one that parallel to you is nadir to you and zenith to you, yes. But what about the side fields? Yes, there are, but it is negligible. So that is the reason we say that, okay, we simplify this. Note in space mechanics, we have also learned this. This is your practically orbital frequency. Square root of this. So you can rewrite this actually. You can plug this in. This term, you can plug this as in terms of orbital frequency. Now what I'm going to do is this. We have already learned or rather developed our Euler equation of motion. Roll, pitch, and yaw. What I'm going to do, the one that we have learned before, or the one that we have discussed before, is without the gravitational term. I'm going to do today, I'm going to plug this term and insert into that Euler equation of motion. Shall we see that? Remember this? There you go, this term. Now, if you look back to your exercise of Euler equation of motion, your z-axis, your axis remains the same, right? Did not change. But your x and y have changed now. Especially you have a term here, this one, and this term. This practically is coming from the gravitational equation that actually that we have discussed. All right. So now you have an Euler equation subjected to the gravitational gradient. This is a complete equation which is subjected to the gravitational gradient, and we have also known that pitch is always decoupled, and roll and yaw is coupled motion. I think you have learned this characteristic equation in control engineering. I use an operator called Laplace. For example, in this case, phi1, I write in Laplace form is s square phi1. That will actually solve this job. Phi3, s phi3, phi1. I can express this equation into Laplace form, and I have roll and yaw motion. I can find the characteristic equation. Just do an open loop transfer function, and then you can find the, please try this, and you can find this characteristic equation. Now, in order for this to be stable, sigma 1 and sigma 3 is what we need to take care. Okay, what it means? It means that if I have a very, let's say, huge I1, that means inertia x. Okay, when I have huge, I can't be stable. So I need to have a balance. Which one will be stable? When I have, let's say, a perfect sphere, that means Ixx, Iyy, Izz all equal. When all equal, what exactly happens? Please go to the equation. When all equal, what happens? It becomes totally zero. So from gravitational point of view, you are absolutely stable when all of them. But can you do a satellite which purely you have IXX, inertia of x-axis, inertia y-axis, inertia principal axis, in the principal axis, IXX, IYY, IZ. The inertias are all same? No, we can't. We can try, but we can't. Okay? So that is the reason it will actually, we have to be very careful of. So if you want to stabilize this is the equation that you want to use, and you can play around with the inertia. You can do that in order for you to get a very stable motion. So there is already a standard plot. If you look at it. Now, if you look at this plot, it says that there's so many unstable pitch, you have unstable roll yaw. Why this happens? You go and look at your sigma and sigma 2. Okay? Sigma 1, sigma 2, you look. When you start sigma 1 and sigma 2, we start actually putting the numbers and then checking back here, then you will arrive to this condition, this graph. There is a very, very small region which is stable. There is a stable condition. This region and this slice here. It says that you can read clearly, roll, okay, the roll must be actually bigger, the inertia of roll must be bigger than yaw, and the yaw inertia must be bigger than pitch. You can arrive to this condition, stable condition. Or there's another one, the pitch inertia is larger than roll inertia, and roll inertia is larger than yaw inertia. You will arrive to these stable regions. So there are very tight regions. You can't do much. You just simply can't do much. Okay. So let's see in an implementation how we do it. We know another important item is that centrifugal force. We know that when you are orbiting, you have centrifugal force, right? The faster that you orbit, your centrifugal force is higher. Sure. Okay, because the omega is higher, omega square, you know, it goes into square. So which means that when it is so high, at one point of time, you are practically, you can nullify the gravitational pull. But unfortunately, that we can't be actually flying too high also, because we need to actually follow Kepler's law, okay, and with the Newton's law, Newton's gravitational law. So based on that, how, if somebody asks you how to actually nullify this gravitational pull, yes, we can fly higher, but it doesn't really mean that actually you are going to nullify that gravitational pull zero. No, it doesn't mean that way. Okay, the higher that actually you fly, finally what happened, you are still subjected to the gravitational pull, but that's why you arrive to an escape velocity. You will go up. So we have actually learned in space mechanics, you have a first cosmic velocity and second cosmic velocity. First cosmic velocity to stay in planet Earth, second cosmic velocity when this goes very, very high, then you are out of the gravitational pull. So in a way, what this tells you, there is very difficult way, there is almost, you can never avoid gravitational pull when you are Earth bounded mission. That's the conclusion. If you want to be not gravitational bounded satellite, when you are orbiting planet Earth, what you have to do is that you just have to escape using the second cosmic velocity. But then you are no more an Earth bounded satellite. So that is a clear thing. So if you were actually say that I'm going to actually stay on planet Earth, so you must respect that first cosmic velocity that you have in space mechanics. Then what comes in? Gravitational pull comes in. So in order for us to do, or rather try to improve our stabilization, then what we do, we try to actually play around with the inertia a bit. Don't forget, now I give you a good example. Assume that we have a very long, rigid body like a rocket. Let's say this is the tail of the rocket, let's say this is the center of the rocket, and this is the tip of the rocket. Okay? Wall, you can see, near the wall. At this point, the pull is higher. Gravitation pull here is slightly lower. Obviously, given the same mass. So, which means that it tends to tilt the body. Which means that when you tilt the body, what you have? You have a rotational motion. When you have rotational motion, that means it's also disturbing our attitude. That's exactly what's happening to our spacecraft. I'll give you a good example how certain small satellites have used this gravity gradient. I would say, well, it is a disturbance, it's disturbing us, but how they have used this actually to stabilize their spacecraft. For example, as I mentioned to you just now, you can try this. You have X, Y, and Z. Okay. So if you look at it, 1, 2, and 3, practically the boom are basically along the yaw. The boom is always along the yaw. So why? Because it will actually increase. It is going to give you a higher X and Y. This is higher. So to give you a higher inertia, so therefore stabilization actually can occur better. So if at all, remember, that is the reason this boom is supposed to be before it launch. When it is launched, then the boom is basically extended just to win the inertia, just to win the total inertia. Then the boom are basically extended. If you have everything intact here, the effect of actually inertia is lesser. So that's the reason they have a boom to try to stabilize the spacecraft. Even this is not a perfect. You can never reach 120, 120, 120. So even then, so you have practically Z axis you are allowing to stabilize, destabilize in fact. Alright, go on. So if you look at actual results, if you look at pitch actually oscillates very, very high. The gravity gradient, this is actually Space Shuttle's performance, but it is also valid for any other spacecraft in terms of the influence of the actual axis in terms of the gravity gradient stabilization. Pitch suffers the highest. Okay, then comes the roll. Then the last is basically going to be the yaw. Yaw will start. You start actually, well, not too bad, but again, as we know, at yaw axis there is no influence, but because of the roll, the pitch and the roll is being affected by the gravitational pull, the yaw is eventually also affected. Why? Because the roll is coupled. Roll is coupled with Y. So if Y is affected, yaw will be finally also affected. Although we have seen just now, in gravity gradient formulation, you have only the roll component, you have the pitch component, you don't have the yaw component. It doesn't mean the side effect happens. This is how the side effect happens. Now, you must understand that when we talk about couple, let's say these two axes are coupled. Let's say this is pitch, this is yaw, and this is roll. Now let's say I'm flying. Okay, flying. Now let's say there is a disturbance acting this way. Let's say clockwise. And you see from there it's clockwise. Okay, and this is roll. When I move here, my roll is here, and there is a disturbance, I say, here, and this disturbance no longer is going to affect the roll. It's going to affect the yaw now, here, because the nature of the disturbance is always, let's say, clockwise. Look, I'm moving clockwise, right? He's going to disturb who? Roll. I'm orbiting, let's say this is planet Earth, I'm orbiting. Disturbing. I'm orbiting, still disturbing, but he's not going to disturb my roll. This time around, the same disturbance is going to disturb yaw. But what about this pitch? Pitch is no disturbance, right? Still is not disturbing. This particular disturbance, it can be anything. So what it means that is the reason that actually these two axes are coupled, vice versa. So a roll disturbance can appear in yaw disturbance as a yaw disturbance. A yaw disturbance can appear as a roll disturbance. That is the reason they are coupled. So a roll disturbance can appear to yaw. So that's why it's being influenced in the way, right? So they are, but pitch is uncoupled, pitch is coupled, but don't forget, pitch has the biggest hit in terms of a gravity gradient when it comes to gravity gradient stabilization. Go on. All right. Now talking about all this, we know that we can use the gravity gradient to even stabilize the satellite. But at the end of the day, what we need to know also, we know for the fact he is actually, if we don't use the inertia correctly, and we don't calculate the inertia correctly, we don't actually do the characteristic equation and evaluate the inertia 1, inertia x, inertia y, inertia z correctly, then we will actually be in an unstable region. So now, not all satellites can do booms like what you see. Booms are available for small satellites, easy, but if you use satellites, you don't have booms. You just build a satellite, then you live with that gravitational disturbances. What you have to know is that you have to quantify the gravitational disturbance so that you can correct it. So what we are going to do here is that we are going to define all those external disturbances that you have in space, which disturbs the rotational motion of a satellite. First, to start with, since we already know the gravitational gradient, same equation I've invoked, the one that actually we have developed, same. A constant disturbance, very important here, is a constant disturbance. Okay, for an Earth-oriented mission, it depends on the inertia and orbit. Constant means what? Like constant. Let's say the magnitude is 1 Newton meter. It will be 1 Newton meter throughout the life of the satellite. There won't be much of oscillation. That's what it means. It's a constant. Okay. So to calculate the quantify, so you have an x, it has a constant, and y is a constant disturbance. Okay. All this in a Newton meter. These are torque. Well, mu, Earth gravitation constant, I is a satellite's moment inertia. Then you have phi1, phi2 is basically attitude deviation. So phi1, phi2, if you can look at how much is the actually attitude deviation that you will have. Okay, what is the deviation normally that you will have? Let's say average about 1 to 1.5 degrees. This is quite a lot. This is the accuracy. Yeah, accuracy, so to say. It's just like when you move this, what is the deviation normally? If the hole is orbiting, normally it is being disturbed 1 to 2 degrees, like that. That's how you actually put it. And RE is a radius of. So you can actually estimate that in constant. Go on. Second disturbance that actually we have is aerodynamic disturbance. Always know aerodynamic is there. So first let me see a constant disturbance as well, just like the gravitational disturbance. However, it is also necessary to consider the atmospheric disturbance, which varies significantly low and high solar activities. Okay, this is important. Now, this disturbance, first I define T as a torque. F is basically a force. Okay, first of all, how to calculate the force? The force is nothing but half of rho. Rho is the atmospheric disturbance and atmospheric density. Atmospheric density at night is smaller. During the day, it's bigger because of the solar activity. So which means that during the day you will have more drag. During night you have less drag. That's what it means. Because atmospheric drag at night smaller, thinner. And the sun face will be bigger. Surface, look at normal to the force. Let's say you're flying. This is your satellite, cubical satellite. This whole surface is exposed to aerodynamic drag. This is what you need to calculate. Okay. Drag coefficient you can take 2, for example. Then the velocity, depending where you are flying. We have learned the space mechanics, then put that particular velocity. use vis Vy equation, you can calculate the velocity. Then the center of gravity of the pressure, that means aerodynamic pressure, where is that? So if you want to actually have it, let's say in the middle, let's say this is the middle center of gravity, your pressure can be maybe high here, depending. If you take a huge cantilever, that means you take a maximum cantilever, that means maximum L, you get the worst case. You put it together, you'll have zero. Huh? You would never have that. Okay? You put it this and this is the same, then you have zero. You won't have any force. No. You take maximum is the best. Okay? You take any center of gravity is here. Take maximum. Let's say the surface is here max. So take maybe the maximum. Okay? And that depends where you take. You take maybe you can calculate that. Huh? Yeah, depending where you take, it can either cause only one axis or two axes, depending how, where, and you take. So that we must be very careful. Okay. Now, this particular axis, if you look at it, it doesn't affect the Z, because you are flying, roll. Basically, sorry, it doesn't affect your pitch. It affects your and it affects your roll. It doesn't affect your pitch normal to the axis. It doesn't. And normal to the surface, it doesn't, because the surface is the force is actually normal to the surface. So pitch axis, you don't have aerodynamic disturbance. Okay, you only will have basically on your roll and your basically your yaw. Okay. All right. Go on. Okay, let's see. Now you have a magnetic field disturbance torque. Okay. Now, as we know that planet Earth has a magnetic field. Now, this magnetic field is going to also disturb us. I also remember that we have also discussed that magnetic torques or other magnetic field can help us to control a particular satellite. How? Assume that you have a permanent magnet, you put into the magnetic field, it can actually move. So assume the permanent magnet is inside the satellite, you put under that particular influence of the whole magnetic field, practically the satellite can move. Okay? So in that sense, the same disturbance, the same magnetic field can be your disturbance also. We can use it to control, but then at the same time, it can be also our disturbance. So we have to know exactly how much that it is disturbing us. This torque is a harmonic torque. Harmonic means what? It is not constant. It has maximum and minimum. Now it has a double of the frequency is actually double of the orbital frequency, which means that it has two peaks. Why it has two peaks? Now assume the planet Earth is this. North pole, south pole is the highest intensity in terms of a magnetic field. So if you start flying up one peak, go down another peak. So you will have like a beautiful sinusoidal graph, a sinus graph, which is nice. Two peaks. So within one period of orbit. So it's important to understand. So there is a and it is also caused by the wires that you have in the satellite. So it's called actually residual dipoles because the wires. So normally what we take is that about 10% of that satellite service we take, it is a cross section of the wire and times by the actual current is going to go through the wire. Normally we take about 1 ampere. So this will be the dipole. But how to estimate the BLVLH? Yeah, this is important. Let us see how to actually estimate this. Okay, now if you look at this, you have Earth magnetic field in local vertical, local horizontal system. Local vertical, local horizontal system. Now B0. B0 is defined as the magnetic moment of planet Earth will be given and at the radius. Now, the further that actually you go, the magnetic field is going to go reduce. Okay, bigger, this drops. Nearer, this will become big. and I is actually inclination. So what it says that when you have an inclination, this is basically 2 times, as I said, this is actually the actual orbit period of the mag. That means the actual magnetic disturbance. The inclination of the orbit is important because when in an equatorial region, it is quite well low, so to say. But if you are in a very highly in a polar orbit, the influence of this is going to be higher because you have a very high intensity of magnetic influence in the North Pole and the South Pole. So it depends on the inclination as well. Okay, and this actually you can plug in and you can find the actual. Now this will be 2 times, 2 times of the orbital frequency. Let's say your orbital frequency 0.001 radian per second, so it will be 2 times of that, so that the sinusoidal graph will be going nicely to us. Okay, go on. Okay, solar disturbance talk. You have this is harmonic as well, so you can imagine you have a good sinusoidal graph. It's influenced mainly by the surface reflection and the geometry. So I define solar torque, force, and again back to the where is center of gravity and the pressure point. So the solar F will be defined as basically CS is the radiation constant. Normally use 1358 watt per meter square. If you learn satellite technology, I think you've been exposed to that in power system. C is the speed of light, plugging there, surface, how much of actually surface is exposed in the body of a satellite towards the sun. That remember when it goes to the eclipse phase, this will be totally zero because there is no sun. Come back to the sun phase, you will have this disturbance. So it is a periodical. Then you have the location of the solar pressure. This can be done just like the aerodynamic torque. So depending on the location. Sometimes if you put at a parallel to the actual axis, you won't have it. So it depends where you want to put, just like I explained just now. If you put parallel to the pitch, for example, then you can't just have a parallel to the roll. In fact, you can't actually have the aerodynamic drag. So you must actually see where you want to put it so that you can have a maximum drag. Alright, then you have a CG, center of gravity. You have a reflection factor, you can use 0.6, and the sun incidence angle. Sun incidence angle is this, maximum will be basically cos. If you look at it, cos 0 will be 1 because it will be directly on the spot. That means no angle, no zero angle, it will be basically just on the spot. So no angle between that. So it's a cos angle, that means direct normal to the surface, that will be maximum. So cos 0 is 1, so it's a maximum. So you can plug in this, it's quite easy to do. Okay. I think 4 major disturbances that actually we need to evaluate. We will do that, and we will do an exercise so that actually you can understand that clearly how to actually do this, so that we can adjust. More importantly is this, to design your system at the worst case as possible. If you're not careful of actually putting the actual pressure point where you may lose, that means the disturbance can be just only acting on only one axis. Just like I've given an example, you can actually do so that aerodynamic drag, for example, you can do such that it is not affecting your pitch. Yes, but that is not the best model. You need to actually make sure that you give a worst case. So the actual alignment where you want to actually put the actual pressure point of these disturbances, especially the aerodynamic and solar, is important so that we can actually design a worst case scenario. So we'll try that in an exercise. Thank you.